In this module, we will consider the reflection and transmission of waves. In general, waves will reflect anytime the propagation speed of the waves changes. The entire amplitude of the wave need not reflect. Some may continue to propagate in the same direction. The amount of the wave that is reflected rather than transmitted depends on how much the speed of propagation changes. Furthermore, reflection can cause a reversal in the displacement depending on whether the propagation speed increases or decreases. This reversal can be considered as a 180-degree phase change for sinusoidal waves. Consider a wave traveling on a string which ends at a boundary. We can consider two ideal limiting cases for how the string is attached to the boundary. First, the string could be completely fixed so that the displacement of the wave at the boundary always vanishes. Second, the string could be completely free to move so that the slope of the displacement of the wave at the boundary always vanishes. We can best understand how reflection works in these cases by relying on our understanding of superposition. Consider the following example where we have a wave which is going to reflect as if it were completely fixed at the boundary. Notice that when the displacement is forced to vanish at the reflection boundary, the wave must invert as it reflects. To consider how this happens, consider superposition of two waves, one inverted, traveling in opposite directions, and set up so that they always cancel exactly at the boundary. We see that this clearly explains why a wave inverts when the wave is forced to vanish at the boundary. Now consider a wave which is set so that its boundary is completely free to move. In this case, the displacement is unconstrained at the reflection boundary and the wave reflects without inverting. In this case, we can consider this as superpositions of two waves, both of which are upright and are completely symmetric about the boundary, allowing us to have a perfectly flat slope at the boundary. We can understand how reflection and transmission behave in general by first understanding how ideal reflection corresponds to waves traveling on a string where the mass per unit length suddenly changes. So ideal fixed reflection corresponds to a normal string being attached to an infinitely heavy string. In this case, the speed of propagation suddenly changes to 0. Ideal free reflection corresponds to a normal string being attached to a massless string. In this case, the speed of propagation suddenly becomes infinitely fast. Now consider a wave traveling on a light string connected to a heavier string where the speed of propagation drops by half. As the wave hits the boundary between the light and the heavier string, we see that we get reflection, which is inverted, and some transmission. It turns out that only about 1/3 of the wave amplitude is reflected, while 2/3 is transmitted. The reflected wave is inverted, while the transmitted wave is compressed because the speed of propagation has dropped. Finally, consider a wave on a heavy string connected to a lighter string where the speed of propagation doubles. As the wave hits the boundary between the two strings, we see reflection occurring. In this case, the reflection is upright. Again, 1/3 of the amplitude reflects but is not inverted. The transmitted wave is stretched because the propagation speed increased and the amplitude increased to 4/3 its original value because the string is so light. In general, reflection will occur for any type of wave anytime there is a change in the speed of propagation of the wave, even if the change in speed is smooth. If the speed of propagation decreases, then the reflected wave will be inverted. For a sinusoidal wave, this inversion can be considered to be a 180-degree phase change. The power in the propagating wave will also be conserved. Any power in the wave that is not reflected at the boundary where the speed of propagation changes will be carried forward in the transmitted wave.